first of the couplers to isolate the signal to the electrical, and then drive the buffer and get resistor and IGBT. So if you drive the high power module, please add buffers between the optocouplers and the IGBT. And for the optocouplers, insulating the control circuit and the main circuit, but please use the high CMR item. So higher DVD to resistance capability is needed for the optocouplers for driving the IGBT. And reverse bias power voltage is negative minus voltage, and positive voltage is applied to the IGBT. But please carefully design the resistance voltage of and malfunction of the power supply. So if the voltage power is not sufficient, so voltage gate drive voltage is dropping during the IGBT. So and gate drive circuit. So this is buffer, and please use a twisted and shortened gate wires to between the gate drivers and IGBT modules. So please minimize this area. So between the buffer and IGBT gate emitter, please minimize this area, and to reduce the current loop or effect of the from the emission noise from the outside. And also please add a tenor diode between the gate and emitter to prevent a surge voltage from the power supply if there are higher voltage. So our guaranteed gate emitter voltage is maximum voltage is 20 volts. So if higher voltage, higher than the 20 voltage applied to the gate terminal, so IGBT easily broken by the higher voltage. So to protect the gate emitter terminal, please add a tenor diode. So we recommend a 20 volt or 20 volt tenor diode to add gate and emitter terminal. And then gate driving current. So to drive the IGBT modules, sufficient power is required for the gate power supply. So to calculate this slide shows the example of the calculation of the gate current. So gate drive current, the peak value is calculated this formula. So if positive gate emitter voltage plus negative gate emitter voltage divided by the external gate resistance plus internal gate resistance. So if you use 15 volts plus 15 volts minus 15 volts, and the internal gate resistance is 2 ohms, so maximum peak current is 15 plus 15 is 30 divided by 2 is 15 amp is required for the gate power supply. So this is example for 15 plus, and if there is a 0.75 ohm and 0.3 internal resistance, so peak current is 28 amp is needed for the gate power supply. This is a peak value, but average value is a little bit different. So average gate current is calculated by this equation. So switching frequency times gate charge plus input capacitance times negative gate voltage. For example, so 5 kilohertz switching frequency and gate charge is 6,000 nanocoulomb, and input capacitance is 180 nanofarad, and negative minus 15 volts. So average current is only 0.0435 amps. So peak current is quite big, but average current is very not so big. So please design your gate drivers based on this current breakdown. So power supply needs a high peak current, but total power is not so big. And gate drive power. So to estimate the driving power, so turn-on power is calculated by this formula. So switching frequency times half of the input capacitance of gate charge times gate voltage. So in this case, 5 kHz, 6,000 nanocoulomb, input capacitance is 180 nanofarad, plus minus 15 volt driving. In this case, total power of the gate turn on is 0.65 watt. So turn off power is the same as turn on power. So the turn off the gate driving power is 0.65 watt. So total gate drive power is sum of the turn on power and turn off power. So total is 1.3505 watt is required for the power supply. So the gate charge, so you can find this value from our data sheet. So our data sheet shows this dynamic gate charge graph. So please refer our data sheet and estimate the gate charge capacitance. So in this case, if we drive from the 0 volt to 15 volt, so this is a gate charge, gate emitter voltage curve. So total, if you drive the IGBT module to 15 volt, so gate charge is 740 nanocoulomb. So if you drive our IGBT module from minus 15 to plus 15 volt, so total gate charge is the sum of the positive gate charge and the negative gate charge. So total gate charge is from here to here. So about maybe 1200 volt nanocoulomb is the gate charge for this IGBT module. And then this is general information about the effect of the gate emitter voltage and gate resistance. So if you increase the gate emitter voltage, so on-stage voltage will be decreased. Also, turn-on characteristics, so switching speed will become faster than the switching characteristics. So switching speed will be decreased by increasing the gate emitter voltage. And turn-on surge, but so higher switching means the turn-on surge, higher turn-on surge voltage. And DVDT malfunction will be, the risk of the malfunction will be increased, and the short circuit resistance capability will be decreased, and the radiation irregular noise will be increased because the switching speed will be increased. And also the effect of the negative gate emitter voltage. If we increase the negative gate emitter voltage, turn-off characteristics switching will be decreased, and turn-off surge voltage. So this is usually different between the AP Weher IGBT and FZ Weher